just a testament to the breadth of people that Jens has advised. Christian has worked a lot on cryptography and peer-to-peer networking. And so Christian was Jens's PhD student. He also worked with Jan and graduated from UCLA in 2006. So take it away.
Thank you, Ben. Again, this is, as Ben said, to show the breadth of Jens's interests in part. I had, in my PhD times with him, two interests in programming language, obviously, and security, and he has always encouraged both. So he now has to suffer through a security talk. And now I know why the clicker didn't work. Okay, so because I'm not speaking to security audience, I want to introduce the people that are going to be starring in our play. And first of all, we're going to have the Walters. Usually you know about Alice and Bob. We're talking about the Walters. Walters are people we trust a little bit, right? And they sign some kind of messages, and they are helping us in the protocol, right? So that's also Walters. They have their own signing keys and they sign messages. And then we have Peggy, and she wants to convince somebody of something. She's the prover. She tries to prove something to some person, right? That's Peggy. And one example that is quite common and that has kind of been the motivation for the original work here was that there's this web of trust where you try to prove that somebody has this PGP key, right? So Peggy has some PGP key, and the Walters have witnessed that, have met her, and can say, okay, this is actually Peggy's key. I've checked, I've met her. She's shown me her passport. And so Peggy wants to convince some other person that she hasn't met in person directly that this is really her key, right? And this person is Victor. He's the one who tries to verify that whatever information Peggy has, that the Walters have presumably witnessed. Okay, that's our setup. So the goal is basically, so we have a couple of people that are trusted by Victor. So some Walters are trusted, right? Not everybody in the world is trusted to validate information. And on the other hand, of course, some people have actually witnessed the thing, the key association or the event. And so they have provided Peggy with that signature. And what we want to find out is what is that intersection. And we want to see how big is the intersection, because if there's only one person, well, maybe that's an attacker and it's bad, but if there's 50 people in the intersection, that's great. So we want to compute the set size intersection of the people that are trusted by Victor and the people that have actually witnessed the statement that Peggy wants to prove. Okay? Pretty easy. Now, the problem is, well, these are basically social relationships, and we don't necessarily like to have all of the information out there. You don't want to disclose exactly who you are trusting. And if it's depending on what it was, maybe you don't want to disclose who has witnessed the event. So, but we want to see the intersection. Right? So we have a privacy problem here. And that was the goal of the fork of trust protocol. Was to basically go and say, okay, the specific statement, yeah, that can be public, but we don't want to discuss who signed it. We don't want to trust, the other party doesn't want to trust who they trust. And we want to get the size of the intersection. Okay, so the fork of trust protocol is therefore the idea of a machine that is, as a machine trusted by Peggy and Victor, or we could say a cryptographic protocol, of course, that converts the valid signatures and the public keys into something equivalent that we can't get back to the original information, but we can use to compute the set size intersection. And I'm going to present a slightly simplified version of the original fork of trust protocol. It had some additional steps in there, which in the end turned out to not matter. They helped defend against some problems, but they didn't, well, achieve the big goal, as we will see. So that's the idea. We will build this fork of trust machine that takes the keys of the people we trust, the signatures, and then we produce something that is equivalent, where we can still check the signatures and so on, but we can't get back to the entities that made the signatures. Okay, and then we can, of course, build trust without disclosing the private information about the Walters. Yeah, so that was the goal. How did the fork of trust protocol work? Well, first step is Victor randomly blinds the set of the trusted public keys he has and gives them to Peggy. Right? So we take the keys we have, we blind them, so Peggy can't get back to it. It's an isomorphism, which means even if she had infinite computing power, she couldn't compute back the original one set, and we give that to Peggy. And then Peggy takes her messages and the signatures and the blinding public keys and blinds everything again with her blinding factor. All right, so it's like double crossing everything. And yeah, she might also permutate the order and stuff like that, details. So it's sets, not arrays, where we can say, oh, fifth position, that's this one. Right? And if we don't want to disclose the size of the sets, we could also pad them with random things. Right? So we could just add random people we trust, and they don't really exist. We just made up some public keys or something like that. OK, so we send that back to Victor. And then basically in a bit of the style of Diffie-Hellman, well, first of all, Victor checks the signatures. And then for the things that Peggy gave for black, well, they were not blinded with his blinding factor yet. So he blinds them again. Right? So now everything has been double blinded. And we can basically see, well, it's double blinded. Well, how big is the intersection of the double blinded information? That's the high-level idea of the protocol. OK. So now, given that we had this JENSFEST coming up, I told his future grandchild that I would want to have a formal verification of this protocol. Let's prove that this is actually correct. And we thought the difficulty was going to be to precisely formulate the privacy properties, given that we still reveal the set size intersection and that there's this padding problem and how big are the sets. And so, yeah, well, as in some sense, some of the most interesting work in type theory is not proving a type system sound, but proving it unsound. Same thing applies in security. If you try to prove the security protocol correct and you find out, it's also a very good lesson. And paper was published by Garcia like 7 years earlier. Nobody found the problem. Nobody bothered formally verifying it either. So, OK. So instead of a proof, you get a disproof. Right? OK, so how does the attack, well, we have two attacks. How does the first attack work? Well, we first want to find out who are the people, who are the Walters that signed the statement on Peggy's side. And so the first thing is of course, Victor cheats. And he doesn't blind everything the same way. He just uses a different blinding factor for every one of the keys. Right? So poor Peggy, of course, follows the protocol, right? Sends back the double-blinded information. And then what our attacker does is simply, OK, now he has to blind everything with all of the blinding factors he used. And if he finds a match, then he can go and say, well, that one had to be this one in my original set. And given that these are isomorphisms over very, very large groups, think 2 to the 250 elements, something like that, it's basically, if there is a match, well, he can be very, very certain that this is the right one. Right? And so thereby, he can basically follow back the chain and say, OK, this is one of the people who signed it. And so as long as he has an idea, I suspect maybe this Dennis guy, he was the signer, he puts him in his set as trusted, blinds him in a specific way, and if it comes back and after, unblinding on backlist, there is a match on this with this particular unblinding factor, he knows it was Dennis. OK. So we said, OK, well, that's bad, but maybe it's only half bad because at least whoever Victor trusts is still protected. OK. Second attack. We want to find out who Victor trusts. And this one is a bit more specific. The fork-off trust protocol was instantiated using BLS signatures. And it's the only instantiation we know of, so we have to go a little bit into detail of how the cryptography worked here. And, a bit unusual, it requires actually that the Walters collaborate with Peggy against Victor. Right, so it's usually thinking of different entities, but of course in a security analysis, you can't just say, nobody collaborates against, And so the situation is basically, you want to find out, Dennis wants to find out, does Jens trust me? Am I in his set of trusted things? I'm going to have Jens run this protocol with Christian, and we're going to find out if I'm in his set. So I'm happy to work with Christian against Jens. That's the idea here, right? Collaboration. OK, I have to give you a brief introduction on BLS signatures. Who here knows already BLS signatures? Oh my goodness. Well, fortunately, in my view, it's the simplest signature scheme we have if you look high level at the theory. It's the worst to implement, but from the theory, it's actually the simplest one. So I tell my students in crypto exams, if the examiner asks you, give me, explain to me some signature scheme, always use BLS, right? Okay, so what do we need? We need a multiplicative group of some prime order P. I always have some groups. And there has to be some generator we've all agreed on. Let's call it gamma. Have some hash function that hashes elements into that group. And the complicated thing is we need a non-degenerative bilinear map. Non-generative or non-trivial means not everything is mapped to 1, or the neutral element. And it's bilinear, which means we have 2 arguments, and basically it's multiplicative in both, so we can pull the exponents out. Those things exist. If you implement them on top of elliptic curves, the implementations get horrible, evaluation E is expensive, but we can believe, okay, these kind of things exist. So, now, we take a scalar, just a number modulo P, that's our private key. The corresponding public key is the generator to the power of X. Also easy, right? And then the signature, if we want to sign a message, well, we hash the message to the group and then raise it to our private key. Well, very easy signing. And if you want to check whether a signature is valid, well, we take the signature and the generator, evaluate it under the bilinear map, and check if that's the same as if we take the hash of the message and the public key under the bilinear map. And if you just fill in the equations I put on top and pull out the exponents, you'll see that those two things should be the same. And if you then take a DDH assumption on the groups, you can find out that, okay, it would be difficult to produce one of those if you don't have the private key. Okay, so why are BLS signatures fun? Well, we can use them for blinding. So if we have the situation where we have a private key X and a signature, and we take us a blinding factor B, again modulo P, what we can do is we can basically raise our public key to the B and raise a signature to the B, and it will still match because it's bilinear. So we can blind the public key, get a new public key, and it's clearly a discrete logarithm problem to go back. And we can take a signature, raise it to the same blinding factor, and the signature will still sign the message for the blinded public key. Oh? Okay, so now how does this help us find out who Victor trusts? Well, let's assume that Victor has a set of people they trust, and he has picked some blinding factor that he's going to use to blind it, and so he's going to send out as the blinded set to Peggy, the public keys of the people he trusts, raised to the B. And again, here we assume that the Victor is the honest guy, right? He's just following the protocol. He's not trying to attack us by picking different blinding factors. Okay, so now what we assume is the interesting assumption, well, Peggy has access to the private keys of the Walters. After all, they're conspiring, right? So now, what can she do? Well, she can basically, if you have a private key, there's a group. Group has a group order, which means there's an inverse. So you can compute the inverse of the private key and multiply everything she gets from Victor with the inverse of the private keys. And if they match, it basically gives her gamma to the blinding factor. And then she can go and say, those two match, and I get this gamma to the blinding factor. And now I can, of course, just iterate. I have determined the blinding factor. I can raise gamma to the B. Well, I haven't determined B. I've determined gamma to the B. But I can raise that to the private keys, and I'll find all the people that I've conspired with, whether they are in the set. Right? The only prerequisite I had is that basically 2 of the people that were trusted by Victor were in conspiration with Victor. And then it's completely game over. Okay, so to conclude, first of all, the protocol has fatal flaws that we don't really know how to fix. Right? So it's supposed to protect privacy, and on either side we can break it. In one case with a bit of stronger assumptions, but that's still too bad. Second part is, well, this was very useful to attempt formal verification. So thank you, Jens, for breaking yet another protocol. So it's actually useful to do this stuff. And overall, I would say one conclusion is we need to keep a very open mind on adversary capabilities. The idea of, Victor conspiring with the vouchers and them handing out the private keys, yeah, this is fun. And we've seen before in the literature some other papers where they were doing some privacy protocols, triple Diffie-Hellman, and where also, if this privacy key is compromised, which wasn't exactly in the original people's mindset, then very, very bad things can happen. Right? And so, keep an open mind on this. We actually also saw something similar with TLS. You all know about TLS at least, right? So TLS 1.3 was developed with formal proofs, and they really went and said, okay, we have first version of TLS that has a formal proof in it, and then a couple of months later, and I always told my students, well, be careful, formal proofs is great, right? But you can't be sure that that's everything, right? And a couple of months later, a paper came out basically saying attack on TLS 1.3, and what they had done is they had used an attack that wasn't covered by the formal proofs. It wasn't covered by the adversary mod. Yay. Right, so formal proofs, great, but make sure you prove the right thing. Thank you.